Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into a classic coding challenge that can really trip you up if you're not careful.
Yeah.
The binary tree zigzag level order traversal.
It's one of those problems that seems straightforward at first, but then the zigzag throws a wrench into things.
Exactly. So for our listeners who might be encountering this for the first time, let's break it down.
Okay.
Imagine you have a binary tree,
Right.
a classic data structure with nodes connected in a hierarchical way.
Mm-hmm.
Our goal is to visit every single node in the tree, but not in the typical level-by-level order.
Right. Instead of going straight across each level from left to right, we need to traverse in a zigzag pattern.
Okay.
So we go left to right on the first level, then right to left on the second level, back to left to right on the third, and so on.
I like to think of it like reading a page.
Okay.
But instead of going left to right on every line, you alternate directions with each line.
Yeah.
You end up with this sort of weaving pattern through the tree.
That's a great analogy. Now, I know what some of our listeners might be thinking. Can't we just do a regular level order traversal and then reverse every other level?
Yeah, that's what immediately came to mind for me, too.
Yeah.
It seems like a simple enough solution.
Uh-huh.
What's the problem with that approach?
Well, it works, but it's not very efficient.
Okay.
Think about it. Reversing an entire list of nodes takes time, especially if you have a wide tree with tons of nodes on each level.
Right.
That extra reversal step adds unnecessary complexity.
So the brute force method gets us the right answer, but it's not the most elegant or efficient solution.
Right.
What are some smarter ways to tackle this zigzag traversal without all that extra processing?
That's where things get interesting. There are a couple of approaches that are much more efficient and, dare I say, elegant.
Okay.
One common technique is to use breadth-first search, or BFS, but with a little twist, a direction flag.
A direction flag. Okay, I'm intrigued. How does that work?
Well, imagine you're starting at the root node of your tree. Your direction flag is initially set to, let's say, left to right.
Okay.
This tells you which direction to process the nodes on the current level.
So we visit the root node, do whatever processing we need to do, and then add its children to the queue, just like in regular BFS. What happens next?
Here's the key. Before moving on to the next level in the queue, we flip the direction flag to right to left.
So when we start processing the children of the root, the flag tells us to go from right to left. So we'd visit the right child, first add its children to the queue, then visit the left child, and so on.
Exactly. And then before moving down to the next level, we flip the flag back to left to right.
So essentially, the flag is acting like a conductor, orchestrating the order in which we process the nodes in the queue.
Right.
It's simple but brilliant.
It really is.
And the beauty of this approach is that it integrates seamlessly with the standard BFS algorithm.
Yeah.
You're just adding this tiny bit of logic with the flag to get the desired zigzag order.
Exactly.
Okay, that's one pretty neat solution. What are some other ways we could achieve this zigzag traversal?
Another interesting approach uses two stacks instead of a single queue.
Okay.
We can call them, say, current level and next level.
Two stacks. Okay, now we're talking. I'm already picturing how this might work, but walk me through it.
Let's start by pushing the root node onto the current level stack.
Okay.
Now imagine we're processing this level.
Mm-hmm.
For each node we pop off current level, we're going to push its children onto the next level stack.
So far it sounds a bit like BFS, but instead of a queue, we're using a stack.
Yeah.
Where's the zigzag magic happening?
It's all in the order we push those children onto the next level stack.
Okay.
If we're on an odd-numbered level, we push the left child first, then the right child. On even-numbered levels, we reverse that order, right child first, then left.
I'm seeing the light now. By controlling the order in which we push the children, we're essentially setting up the next level to be traversed in the opposite direction.
Precisely. When we're done with the current level stack, we simply swap their roles. The next level stack becomes the new current level, and we repeat the process.
So we're kind of pre-building each level in the desired order before even processing it.
Yeah.
It's like a carefully choreographed dance of stacks.
That's a great way to put it. Now, are you ready for a slightly more advanced approach?
Oh yeah, bring it on.
It involves a data structure called a deque, or a double-ended queue.
Ooh, a deque.
Yeah.
I've heard of those, but I haven't had a chance to use one in a real problem yet.
Yeah.
How does a deque help us with this zigzag traversal?
Well, a deque is special because it lets you add or remove elements from both ends.
Okay.
It's like a queue and a stack roll into one.
So we can use it like a queue when we want to process things in a first-in, first-out FIFO manner, and like a stack when we want last in, first out.
Hmm.
LEF.
Exactly. And that versatility is what makes it perfect for this problem.
Gotcha.
We're going to leverage both ends of the deck to control the direction of our traversal.
Okay, my brain is ready.
All right.
Tell me how this deck magic works.
Imagine our deck as a train with doors at both ends.
Okay, I'm visualizing a very fancy train.
We start by putting the root node into our train. Now, if we want to traverse left to right, we'll add children to the back of the train, but take them off from the front to process. This way, we're effectively treating it like a regular queue.
So first in, first out for a left to right level. Makes sense.
Now, when we want to go right to left, we just reverse that. Add children to the front of the train and take them off from the back to process. Now it acts like a stack.
Clever. So by switching which end we use for adding and removing, we're controlling the direction. Do we need a separate flag to keep track of which direction we're going, like in the BFS approach?
We could use a flag, but there's an even neater trick. We can just use a single variable that toggles between 0 and a none for left to right, 1 for right to left.
Ah, I like that. It's like a little switch that flips the behavior of our dig train. It
Yeah.
seems like with Deques, it's all about choosing the right methods for adding and removing elements at the right time.
You hit the nail on the head. And that's the heart of algorithm design, isn't it? Choosing the right data structure and manipulating it effectively to solve a specific problem.
It's amazing how something as simple as a deck can lead to such an elegant solution for a tricky traversal like this. I'm starting to see why decks are so powerful. So we've explored 3 distinct approaches now. BFS, with a direction flag, 2 stacks in the deck. Before we wrap up, can you give us a high-level comparison of these methods? What are the trade-offs?
Sure. All 3 approaches, when done right, have the same time complexity. They all visit each node once, so the time it takes grows linearly with the number of nodes in the tree.
So no matter which approach we choose, we're looking at roughly the same performance in terms of how the algorithm scales. What about space complexity? Do they all use the same amount of memory?
Space complexity is also similar across the board. In the worst-case scenario where you have a very wide tree, all 3 methods might need to store an entire level of nodes. So the memory usage also grows proportionally to the number of nodes.
So if they're all pretty similar in terms of time and space complexity, how do we decide which one to use? Does it just come down to personal preference?
That often plays a big role. Some people find the duck approach very elegant and concise. Others might prefer the 2 stacks approach because it's easy to visualize and understand the logic behind it.
And I guess BFS with a flag is a good option if you're already comfortable with BFS and just want to add that little directional control.
Exactly. Sometimes the best approach is the one that clicks best in your mind, the one you find easiest to reason about and implement.
I love that there isn't one right way to solve this.
Yeah.
It's more about understanding the nuances of each approach and choosing the one that best suits your thinking style and the specific needs of your project.
Absolutely. It's about having a diverse toolkit of algorithms and data structures and knowing when to apply each one effectively.
Well, I feel like we've covered a lot of ground today. We've gone from the basic idea of a zigzag traversal to exploring 3 very different ways to implement it. Before we wrap things up, is there anything else our listeners should keep in mind when tackling this problem or similar tree traversal challenges?
One thing that always helps is to visualize the process. Draw the tree on paper and walk through each step of the algorithm, seeing how the data structures change and how the traversal unfolds.
That's great advice. Sometimes getting it out of your head and onto paper can really clarify things.
No.
Another tip I'd add is to think about edge cases. What happens if the tree is empty? What if it's skewed to one side? Testing your code with different scenarios will help you catch any potential errors.
Excellent point. Thorough testing is crucial for any algorithm implementation.
All right, I think our listeners are well equipped to tackle those zigzagging trees now.
I hope so.
Before we sign off, I have one final question that's been nagging at me.
I'm all ears.
We've been talking about traversing the tree in a zigzag pattern. But what if we wanted to visit the nodes in a spiral pattern instead? Down a level across, up a level across, and so on. How would we adapt our approaches to handle that?
Ooh, that's a great question. And a common variation on this problem, it adds a whole new level of complexity.
I was thinking the same thing. A spiral pattern seems way more intricate than just alternating left and right.
It definitely is. But the core concepts we've discussed today are still relevant. We still need to manage the direction of our traversal, but instead of just 2 directions, we have 4. Down, right, up, and left.
So our trusty direction flag would need more states, or we'd need a more complex way to manipulate our deck.
Exactly. We'd need a way to keep track of which direction we're heading in and when to switch. We might even need to track things like the boundaries of each spiral level to know when to change direction.
I can already see how that would require more intricate bookkeeping and potentially some additional data structures to manage all that information.
You're spot on. It's definitely a challenge that deserves its own deep dive.
Well, that's an adventure for another episode. My brain needs a break after all this zigzagging.
Mine too. It's amazing how a problem that seems so simple at first glance can lead to so many fascinating variations and challenges.
That's the beauty of algorithms, isn't it?
Mm.
There's always something more to explore, always a new twist or a new challenge to keep us on our toes.
I couldn't agree more. And who knows what other fascinating traversal patterns are waiting to be discovered out there.
I guess we'll just have to keep diving deep into the world of code to find out. Thanks for joining us on the zigzagging journey, everyone. Until next time, happy coding.
Yeah, it sounds like you're already thinking about how to solve that spiral traversal.
A little bit. But for now, I think it's safe to say our listeners have gotten a solid grasp of this zigzag traversal.
Yeah, for sure.
And hopefully we've sparked some curiosity about different ways to explore and manipulate binary trees. It's such a fundamental data structure in computer science.
It really is. Understanding tree traversals opens up a whole world of possibilities for solving all sorts of problems.
Absolutely. From search algorithms to game, AI trees are everywhere.
And the techniques we've discussed today using flags, stacks, deques, those are powerful tools that can be applied to many other algorithm challenges as well.
That's what I love about these deep dives.
Right.
We're not just learning how to solve one specific problem. We're building up a mental framework and a set of tools that we can apply to a whole range of situations.
Exactly. It's about developing that algorithmic intuition and becoming more comfortable thinking about problems in different ways.
Well said. I think our listeners are well equipped to tackle those zigzagging trees now, and maybe even start thinking about how to conquer those spirals.
I hope so. And if you're eager to put your newfound knowledge into practice, be sure to check out the show notes for links to code examples and further resources.
And as always, keep those algorithms sharp and those coding skills honed.
Until next time, happy coding, everyone.
From all of us here at AI.Code.Cast, thanks for joining us.